Hi, this is Mrs. Villette, and in this video I'm going to go over your optimization intro and how to find the minimum cost using calculus. I'm not going to fill in the table, I'm just going to start with a review of the function that we're going to use to represent this situation. So in this situation we're going some distance along the road that the station is on, and we're going to then take off and head straight for the house after that. The sort of extreme cases were to just go straight to the house from the station, or to go all the way along the road until you're kind of right behind the house and then go to the house itself. So we've already calculated the endpoints for this situation, and those are in the tables, and we're trying to see if we can get a better place to go that would lower our cost. So let's go back to that sort of intermediate situation. In this situation, I'm going to let x be the distance I run along the road, which makes this smaller leg of the triangle 5 minus x. And then we'll let y be the distance that I go from the road to the house. So I can see that my cost would be 1,000 x plus 2,000 y. Right now that cost is a function of both x and y, but we should be able to somehow eliminate this y variable and write everything in terms of x. So that's what we call the constraint equation. This first equation is called our fundamental equation. So that's the equation that we're trying to optimize, or the quantity we're trying to optimize. Our constraint in this case is just the Pythagorean theorem. It's that 5 minus x squared plus 2 squared equals y squared. So we can calculate that y is the square root of 5 minus x squared plus 4. Now we can write our cost just as a function of x. Our cost as a function of x is 1,000x plus 2,000 times y, but we're writing this y in terms of x. So there's our cost equation. If we now look at the graph, in Desmos I have plotted this cost function, and we can see that there is a local minimum in the middle of the domain of this function. Remember, we checked the endpoints, so this first endpoint was just going straight from the station to the house. This second endpoint was going all the way along the road and then straight to the house once we reach kind of the place right behind the house. What I want to show you now is how I can figure out where this local minimum is using calculus. We're going to do what's called the closed interval method for extrema. And the first part of the closed interval method is just evaluating the function at the endpoints, which we've already done. The second part is to find the critical numbers. So that means we need to find our c prime of x. The first part is easy. The derivative of 1,000x is just 1,000. The second part, we're going to do the chain rule. So we're taking the derivative of the square root function, which is 1 over 2 times the square root function. And we're multiplying that by the derivative of the inside. The derivative of the inside is 2 times 5 minus x times the derivative of negative x, which is negative 1. So let's do a little bit of simplification here. I can cancel this factor of 2 because everything's a multiple. And I'm going to factor 1,000 out of everything. So that gives me 1 plus, then I have negative 2 times 5 subtract x over the square root of 5 minus x squared plus 4. And you'll notice I left a little bit of space with that 1 because what I need to do is get a common denominator. So I need to build up to that common denominator, which involves essentially multiplying the top and the bottom of this 1 by this square root function. Okay, so let's see where we are now. Here is our simplified first derivative. We want to find the critical numbers, which means we need to find the places where this function is undefined or 0. There are not going to be any places where this function is undefined because the denominator contains the square root of 2 squares. And these squares are always going to be positive, so that means I'm never going to get a 0 in this denominator. So what I really need to do is just set this numerator part equal to 0. 1,000 can't equal 0, so we don't need to worry about that part. I'm going to go ahead and rewrite this as equals 10 subtract 2x. I know that I was going to set this equal to 0. So I'm just going to move that linear term over, and then I am going to square both sides. Now this could possibly introduce what are called extraneous roots, so we'll have to check at the end whether our answers actually make sense. And on the right hand side, I need to FOIL that binomial. Okay, looks like I have a quadratic equation now, so I want to get everything to one side, 0 on the other. Now I've got this quadratic function set to 0, and it doesn't look like it's factorable, so I'm going to go ahead and solve for the critical numbers using the quadratic formula. So minus b plus or minus the square root of b squared, which would be 900, minus 4ac, all over 6, so 2a. And when we simplify that, we get x equals 5 plus or minus the square root of 48 all over 6. At this point, just go ahead and simplify that, and you get x is approximately 3.845. That's when you do the subtraction, and when you do the addition, you get 6.155 approximately. Given the context of our situation, the house is only 5 miles down the road from the station, so that second answer doesn't make sense. So this is our only critical number. Given that we've already evaluated the function at the extremes, so at 0 and 5, we can see that our critical number matches the number that we got here in Desmos, and then the only thing that we need to do is just plug that function back into, plug that value back into our function, so into our c function. So c of 3.845, that would be 1,000 times 3.845 plus 2,000, and hopefully you get the idea. We're just plugging this into the function that we came up with, and that should evaluate to be approximately $8,464, which compared to our other two values of $9,000 and $10,770 is clearly the cheapest option. Again, Desmos finds that maximum for you automatically, but this part right here where we're taking the derivative, solving for the critical number, along with evaluating the function at its extremes, is the justification that this is the correct x-coordinate and that it is indeed the minimum value of the function.